Hello, everyone. My name is Brad Erickson. I'm director of the Mayo Clinic AI Laboratory. With me are Shahryar Faghani and Puriya Roserook. Today we're going to talk about uncertainty measurement and specifically a technique that's been developed here for estimating the uncertainty in large language models for retrieval purposes. Uncertainty is a critical concept to get a handle on when one wants to do decision making. Famously, Donald Rumsfeld, the former Secretary of Defense for the United States, talked about known knowns, known unknowns, and unknown unknowns. Now that may seem overly complex, but it's actually valuable to think about how uncertainty enters into decision making. I won't go into it a lot more, but I hope that you'll start to think about how does uncertainty represent itself and how does that apply to deep learning. Large language models have become quite popular over the past few months and years, and that's because they have such an incredible capability to seemingly understand what text documents and interactions with humans represents. A particular technique within large language models is called retrieval-augmented generation. This is something where you provided a set of documents and it will return answers to specific questions that you have for content that should exist within those documents. Now, a challenge with large language models is that it's always going to give you an answer. And while it may say, I don't know, if it has some idea that an answer exists, it will say, here is the answer. And again, that lack of potential uncertainty is a challenge, particularly for things like medical decision making. So, we want to delve into this topic a little bit more and discuss the whole concept of uncertainty, and then we'll talk about how we think that there is an approach to dealing with this challenge. So first of all, I have a few questions. I'm going to point first to Shahryar and ask, what is uncertainty quantification?
Yeah, so that's a great question. I guess all of deep learning models, like computer vision models or large language models, output some numbers which resemble probability and likelihood, but actually they're not. And the reason is that these outputs are not well calibrated. And even though we can calibrate these outputs, but still we cannot address the underlying uncertainty, because at most these numbers can be considered as point estimates. And the thing which is we're going to consider as uncertainty is the interval of those predictions. So that's why we need some techniques to discover and demonstrate these uncertainties. This is where uncertainty quantification comes in to reveal these uncertainty in the predictions of deep learning model.
And is there only one type of uncertainty quantification technique, or how should we think about UQ?
I guess there are many form of categorizations, but I guess one popular form of categorizations is we can divide uncertainty quantification techniques into two broad categories. One, we can call them frequentist point of view or frequentist approach, and the other one is a probabilistic approach. In frequentist approach, we're going to focus more on the data distribution, and we're going to learn from the data distribution without any prior assumptions. But with probabilistic approach, we're going to have some prior knowledge and we're going to input those knowledge. And if I want to count some of the well-known probabilistic approach, I can point to Bayesian approaches, ensembles, and evidential deep learning. And there is another framework within frequentist approach, which is called conformal prediction, which we focus in this project.
Okay, well that raises the next question of why did you pick conformal prediction?
I guess conformal prediction has a lot of advantages over the other uncertainty quantifications paradigms. And so if I want to name few of them, one is it provides statistical guarantees with its predictions. And what do I mean by that? It really gives you a prediction set, and it will make sure that the correct answer exists in that prediction set. So this is one actual benefit of conformal prediction. The other benefit is that it's model agnostic. You can really apply conformal prediction on any type of model. It could be computer vision, classification, segmentation, even generation, or in large language model. And for example, in this case, we applied it on retrieval-augmented generation. And the other fact is conformal prediction is a post hoc method. You don't need to train your model in a way that you can use it with conformal prediction. Actually, you can have a trained model, already trained model, and on top of that, you can apply conformal prediction.
Great. And just for those of you who are in the medical field and want to try to relate that concept to medicine, we often talk about a differential diagnosis where based on the inputs, here are the list of things it could be. And so when you talk about your prediction set that comes back, that's essentially the differential diagnosis. The distinctive is that there's a guarantee that the correct diagnosis will be in that list.
Exactly.
The list may be very long, or it may be very short if you have high confidence in that one thing. So that's obviously a very valuable concept for us in medicine to know that the correct answer is somewhere in that list. I'm going to pick on you now for a while, Puriya. So why is UQ important for retrieval-augmented generation and document summarization?
Well, retrieval-augmented generation has attracted a lot of attention recently, and that is because it's a very powerful method to help LLMs be grounded in some already known knowledge. However, when you look at the process more carefully, you will find some nuances that the user need to deal with before they can apply RAG in a trustworthy manner. One of these nuances is that say you ask your LLM a question and then your RAG pipeline goes and look for the most relevant documents to that question in your database. And what it does behind the scene is that it sorts out all those documents according to how relevant they look like to the question that the user queried. But when you have this sorted out list of documents, how are you going to decide how many of those should you return to the downstream LLM for asking it to generate the questions on top of those? And this is one of the hyperparameters that most people just choose something arbitrarily for. But what we did with conformal prediction is that now we added some meaning to this selection. We basically asked the model to look at those number of documents that we know are going to contain the true answer to the question with a certain level of certainty that the user is looking for. So for example, if you are looking for a certainty of 0.9, we might return 10 documents out of the 1000 available to the model to it. But if you say that I want to be 0.99 sure about that, we might need to return maybe double size of the documents to you. So that is going to be a larger number of retrieved documents because you want to be more sure, more certain about the answer. So RAG without conformal prediction or uncertain quantification in general has a lot of hyperparameters that people are not sure how to pick, but conformal makes that now more meaningful and based on the preference of the user.
So there are a lot of different RAG techniques out there. You mentioned that there are a lot of also different hyperparameters where people tune it according to their intuition about the right way to set them up. Can conformal prediction be applied to any type of RAG pipeline, or are there restrictions on how it can be used?
No, actually, it can be applied to any type of those. So you see, RAG pipelines are very different. Many different variations of that have been developed. For example, we have commercial models used for RAG, open source models used for RAG, and then you also have many different tricks and advanced kind of pipelines that are using RAG. For all of those, you could apply conformal prediction to that. So the advantage of this technique is that, as Shahriar already mentioned, it's model agnostic and it's post hoc. So you basically can just add it as another control knob for your pipeline and then rest assured that the rest of the pipeline could remain unchanged for you. So it's very, very flexible.
Excellent. Now, there are many steps in implementing a RAG system. You got to collect your documents, tokenize them, ultimately embed them, store them in a database, and then you've got to have your question that also then gets tokenized, embedded, and you do some sort of matching to get your solutions. So where does conformal prediction show up in that whole process?
Sure. So all those steps that you mentioned, we can kind of categorize them in two major categories. The steps that belong to the retrieval phase and the steps that belong to the generation phase. And by generation, what I mean is that when you finally retrieve a collection of documents, your LLM is going to look at them and try to answer your question based on those. Now, this technique that we have developed is going to be applied to the first category, which is to the collection of steps that together form the retrieval phase. So we are going to add conformal prediction to make sure that all in all, the retrieval set for the model to look at are going to contain the true answer to the question with the certainty level desired by the user. So it's mostly focused on retrieval. However, we could also apply conformal prediction to the generation, but that is beyond the scope of this specific project.
Okay, thank you very much.
Yeah.
So Shahryar, how might you use conformal prediction in order to select the known knowns, the known unknowns in a RAG pipeline?
Okay, thank you. So I guess before I directly answer your question, maybe I need to elaborate more on these matrix, again, known unknown matrix. I guess we can, when we're talking about a model, we can have a 2x2 matrix. One time we are looking from the model point of view, and the other time we are talking about our expectations in the real world. So then we can have known unknown from the model point of view and known unknown from our expectations. So let's talk about a simple application of it, and then we can apply it to our current project. So let's imagine that we are talking about a computer vision model. It's a classifier model, and it's a chest X-ray classifier. And this chest X-ray classifier has an out-of-domain detection component to it. So if I show it a chest X-ray which has a pneumonia, and it says it has a pneumonia, so it's a known because the model gave us a correct answer, and it knows that it knows the answer. But what if I show a chest X-ray and it rejects it, and in other words, identify it as out of domain? So it's an unknown known. You know, our expectation is that these models should do a prediction on this specific case because it's a chest X-ray, but the model rejects it, which means that the model is unaware that it can do on these specific sample, right? So then it would be unknown known. There is another example which, if I input a brain MRI and it rejects it, so then it's a known unknown, which means that the model knows that it should reject this specific sample because it's not a chest X-ray. But what if I input a brain MR and it says, okay, I'm gonna do a prediction? Well, then it's gonna be an unknown because the model is not trained on brain MRI. So we expect that the model rejects it. But if it doesn't, it means that the model doesn't know that it should reject it. So this is a simple example, maybe not too simple, but a simple example. And now if we want to apply it to our pipeline, which would be the retrieval-augmented generation, we're going to talk about a prediction set of retrieved documents. So we're going to start then with the length of the retrieve set. So if the length of the retrieve set is bigger than bigger than 0, there are two possible options. One would be the model is working fine and it is returning correct documents. So known, returning correct document. But what if the model returns some incorrect document? Then it's an unknown because the model is not aware that it is returning incorrect documents. And in our paradigm of using conformal prediction, these would not happen if you use a correct calibration set to calibrate the conformal prediction. So again, this would not happen if we use a correct calibration set. But what if the return set is equal to 0? Then there are two possibilities. One would be known unknown, which means that the model returns nothing because it is supposed to do that. It means that the correct document is not provided within the provided document, right? So then the returned length should be equal to 0. So which means that the CONFLARE pipeline works fine, right? But what if, again, the model returns nothing, but it has the information? So then it's an unknown known, which means probably there is some malfunctions in the embedding functions because we couldn't retrieve the correct document. So in this way, if we use this algorithm, probably we can identify when the model is doing known, unknown, or known unknown, or unknown known.
Very good. There was a little bit of jargon that got thrown in there. Out of domain. Describe that, and what do you mean by a domain?
Well, so this is a really hard question. I guess there are many ways that we can identify out of domain. One would be, again, from model point of view, and the other one would be from our expectation. And again, the problem is that our expectations are not the same across all the humans. So for example, if we trained our chest x-ray on pediatric chest x-ray, then is an adult chest x-ray an out of domain, or is it in domain, or is a chest CT out of domain or in domain? So again, there's a lot of variability in human interpretation of it, but there's another way of thinking about out of domain distribution, which we can think of the training set. So if we have something which is not well represented in the training set, and probably the model will going to predict incorrect predictions on these kind of samples, then probably it's another way of thinking to categorize samples into in domain and out of domain. But I guess a really hard question.
Maybe I'll throw an extra question in here, edit this out. But so oftentimes when people use RAG, they say, if you don't know the answer, just say no. How would that compare with using uncertainty quantifications? What might be the benefit of using UQ as opposed to saying, just tell me if you don't know?
So then I guess the main advantage of using uncertainty quantification, specifically the CONFormal technique, is that you're going to be sure that the no is real no. And you're going to be sure that the yes is a real yes with a specified amount of statistical guarantee. So I guess that's the main difference.
Yeah, I think that goes to your point, Corey, about when you calculate those vectors of how much this content in a document is like the content of this question.
Yeah.
There's going to be some sort of a threshold function that says that is or isn't relevant.
Yeah.
And things are often not so black and white.
Exactly. So basically, when we do that in the regular way, we need to pick a threshold arbitrarily. But the advantage of conformal prediction is that it gives some meaning to this threshold. So you basically calibrate that threshold based on your own preference. Maybe you just first set the threshold to 0.9 and then look at the performance of your RAG pipeline, the CONFLARE pipeline, and you feel that it is doing mostly good or at least reasonably good to your level of expectation. Well, that is good for you. And then the kind of threshold that associates with that certainty of 0.9 is going to be good for you. And maybe someone else uses the same pipeline, the same model, the same data, and they prefer a higher or a lower certainty level. So I believe conformal prediction could add some values, could add some meaning to many unknown parts of the RAG pipeline, conventional RAG pipeline.
So we've talked about the importance of calibration, and that involves having another data set, and particularly in medicine and some other areas, getting enough data is a challenge. What approaches can you do to help make that a little bit less tedious?
Yep, sure. First of all, it's certainly tedious because one thing that we need to ensure of is that the calibration set that we are putting together, all those questions and their correct retrieval, should be similar to the kind of questions that the model is expected to see during inference time. So that's the main assumption behind the conformal prediction as a statistical guarantee. We need the calibration set to be representative of what the model is expected to see when we are testing that. And now there are two approaches that you can create that calibration set. One is the tedious, hard one, as you mentioned, so that one expert, one user sits and design those questions out of some given documents and then also look at the best document that can answer those questions. And the second one, which we also demonstrated in the CONFLARE paper, is that we can ask some LLMs to mimic that process for us. So for example, we can use a very powerful LLM that we all have access to nowadays, GPT-4, and ask it that, hey, you have access to these data sets, go through them and then try to come up with some questions based on each document. And then When the RAG is done for the calibration set, look at all the sorted out documents based on the relevancy to this queried question that you created yourself, and now pick the first document that you believe is able to answer this question. And then using this automated workflow, we can put together very, very large data set of questions and their representative answers. Then we can later on calibrate the model based on that. The only catch is the power of this entire CONFLARE pipeline is gonna depend on the LLM that you use for this creation task and how good it is. So for example, you could have very good calibration sets using GPT-4, but if you switch to a much weaker open source model, for example, the quality of that calibration set might fluctuate, and that might violate the statistical guarantee of conformal prediction. But again, that depends on the application of the users, on what models they want to use for that. So yeah, if we want to look at this package, the pseudocodes for the two main things that this package does is shown here. So again, we are going to split that into two different components. First, creating the questions, and second, finding the best answers to those questions. For creating the questions, we need to go through all the documents in our calibration set one by one. And for each of the documents, create at least one question. You could also create more than one, but you need to have one question. And here, if you're using an LLM, you need to prompt that LLM to make sure that the type of questions that it creates are as similar as possible to the questions that you expect users will ask the model later on. And then in the second phase, you ask the same LLM, or maybe another LLM, depending on your use case, to look at all the retrieved documents for each question. So for each question, you do the conventional RAG once. You look at all the available documents, measure the cosine similarity between each document and the queried question, and sort out all those documents from the highest cosine similarity to the lowest one. And then here comes the second LLM. You ask the LLM to look at all those documents one by one and go until the point that it finds the first document that it believes is able to answer the question. You stop at that point and you take note of the cosine similarity of that specific document and the question. And that is the answer for that specific data point in the calibration set. So we are going to put together a calibration set of questions and the cosine similarity of the question with respect to the first document among all the documents available in the database that answer that question. And when we put together that data, then later on we can calibrate the model based on that. And how do we do that? Say, for example, the user says, I have this new question, unseen question during inference time, and I want the answer for that with 0.9 certainty. And then what you do is that you look back at your calibration set, all those questions with the representative cosine similarities, and pick, for example, the 0.1 percentile of that data that is related to the calibration set, and look for the confidence score or the cosine similarity that you had there. And then you pick that score, and now you go back to the question at hand and say that, all right, I'm going to repeat this process for the question at hand, and now I'm going to keep retrieving all the documents until the checkpoint that I hit the cosine similarity that I got from the calibration set. So on that checkpoint, I'm going to end. In other words, you are going to retrieve all the documents that are similar to the queried questions with a similarity score higher than your threshold. And this way, you are going to achieve a guarantee that with that specific error rate specified by the user, you have collected all the documents that might contain the answer to this question. So the code might look a little bit, the definition, the verbal definition of that might look a little bit complicated, but if you look at the pseudocode and the code that we have provided in the package, that is not complicated at all.
Very good.
Yes. So in summary, again, what does this pseudocode, especially step 4, does is it's going to learn a threshold based on the calibration set. And during the retrieval phase, we're going to use that learned threshold to retrieve the document.
So I hope that you found this discussion intriguing and that you'll want to go and look up our paper, which is out on arXiv. And there is an associated package for implementing this on GitHub. And so now we'll step you through that so that you can hopefully implement this on your RAG pipeline.